All right. Thanks. Well, that's not the plan for today still, and
Okay, still. So
we'll have to
yeah,
talk by Guenter Pilz on which subdirect decompositions are useful. Please, Guenter, whenever you're ready.
thank you. So algebraists, they love decompositions. And if you look around, you can find some decomposition results which are very useful and some others which are not so useful. And I would like to, I wanted to find out what's the reason for success here. And so this is not all my work, it's joint work with Manuel Kauers, my successor at as a department head in Linz. And I would like to go through in certain instances and to find out where we get some successful results. The first instance are very well known to all of you. They are from vector spaces. And if we know that a vector space is finite dimensional if and only if it's a direct product of the underlying field. And this was a useful, very useful, is a very useful result, and was a big success because before one had to struggle around with errors in three-dimensional space or so, and all computations were very ugly because you had to find out with many drawings what really works. Now we know this isomorphism is very easy if you choose a base and if you work, if you introduce coordinates, then you have already the isomorphism, and the isomorphism back is also easy. Sorry, this should be r to the third and not r to something. And the road back is then that you take linear combinations. But even this easy example is not so much liked under category theorists because it's not a natural isomorphism. These isomorphisms depend on the selection of a basis. We might go to integers in number 2. And if we want to do parallel computations, we cannot directly use these concepts of decompositions because the integers are indecomposable. But what we can do is to do additions and subtractions, also multiplication and so on, if in some sets of n, provided n is sufficiently large. And you all know this isomorphism. If n decomposes into p1 to the t1 and so on, then set sub n decomposes into set p1 to the t1 and so on. And the isomorphism is very easy. You take from x the residual classes modular each prime power pi to the ti. And the good thing is we can do all the computations in each component, and we will then end up in this direct product as what we constructed. And what's the way back to sets of n? It's just the Chinese remainder theorem. The nice thing is that you can deal with integers which are small, relatively small, namely smaller than the maximum of all these prime powers. That call this n bar, and we want n bar to be small, and n and at the same time to be big. it's better to start with n bar. So let's start n bar equal to 50, and then n can be 2 to the 5th, as long as it doesn't go beyond 50, 3 to the 3rd, and so on. And this is already bigger than 10 to the 21st. Now, for nowadays computations, a more realistic choice would be n bar 2 to the 64, and the maximal n which we can do is a really, really huge number. One has to take care for the sign of integers, but this is not difficult. And there's an old proverb, whatever you can do in the set in integers, you can also do in polynomial rings. And the idea is here the same. Let k be a field, and instead of working in k of x, we work in a factor, k of x factored by f, where f again decomposes into prime power or irreducible powers. And this should be a polynomial of sufficiently high degree. One uses this, for instance, in coding theory, and f is there usually some x to the m minus 1. Again, we have that the factor k of x factored by f is the direct sum of factors of k of x to the pi to the di, and the isomorphism is the same as before. You take the equivalence class of each polynomial with respect to some pi to the ti. We still have the choice which f we take, and we want to make these factors on the right-hand side of this isomorphism to be simple. And the simplest case would be that they are that one takes pi to the ti as polynomials of degree 1, and all ti also of value 1. And then you get a polynomial f of this type, simply some product of x to the minus k sub I. And it's so easy to find out what's the remainder in the equivalence class. It's just this, that you take the remainder as the value of p at the point k j. So each polynomial is then mapped to an R tuple of elements of k, and we have in fact decomposed the polynomial ring factored by f into the direct product of field elements. And the way back is also very well known. It's just the Chinese remainder theorem. One might ask, what does P of k mean? And maybe this is a good point to look at the difference between polynomials and polynomial functions. If you have a polynomial in some f of x, then there is an associated polynomial function p bar in the usual way. If we let p of f be the collection of all polynomial functions, one sees it's a ring. It's a subring of f to the f, and the association which associates to each polynomial the corresponding polynomial function is an apomorphism. Is it also an isomorphism? Well, if f is finite, then this cannot happen, because f of x is always infinite, and but the number of polynomial functions must be finite. For instance, if we take x to the fifth minus x over z5, then the corresponding polynomial function, p bar, is just a zero function. So one cannot really say polynomials and polynomial functions are more or less the same, but sometimes they are, sometimes they are not. In case of fields, it's easy. Polynomials and polynomial functions are isomorphic if and only if the field is infinite. That's easy to prove. If f is not a field but only a ring, then the borderline between isomorphism and not isomorphism is still unknown. An old result, for instance, of Arthur says that if the additive group of the field is torsion-free, then phi must be an isomorphism. So one cannot apply the so-called principle of comparing coefficients. And it has the effect that one can say mathematicians do not have principles. We have axioms, we have theorems and so on, but no principles. What about decompositions of the polynomial functions? Well, we don't have to decompose because P of f is a subring of f to the f of all powers of f by the map which associates to each polynomial the list of all its values at the elements of f. And it's quite a good idea sometimes to replace polynomials or polynomial functions by this list of values. For instance, if you have to multiply polynomials, it needs much more time to compute the product of two polynomials or the product of two polynomial functions. But if you go to the f to the f, then the product is just a component-wise product. So it's quite easy to make calculations, but at the end we have to go back again. And what's the correct formula? It's just an interpolation formula for polynomials. This can be improved, however, if you evaluate f at some places and to find out what the corresponding polynomial will be. We still can choose the places as we have before, leading to the Cooley-Tucker algorithm. And the key is to do it in an intelligent way. And let's look at an example of the polynomial of degree 5. We can evaluate at k1 equal to 1, which is easy. It's just the sum of all coefficients. And if we take the value at -1, we get just the alternating list of A0 minus A1 plus A2 and so on. And if you if you evaluate the A0 plus A2 plus A4, the even A's and the odd A's, then P bar of 1 is just the number of the even and the odd ones, and P bar of -1 is just the difference. So we can make advantage of the fact that we can choose the places where we evaluate, and 1 and -1 is a very good idea. If f is the field of complex numbers, we might continue with I and -I, and in general, we might continue with roots of unity. Suppose our field has enough n roots of unity. For instance, finite fields have this property, the complex numbers. Then there's also a primitive nth root of unity, and all the other roots of unity powers of this primitive root omega. And so we decide if omega is a primitive nth root of unity, we might evaluate P at all powers of omega. Then a polynomial A in bold faces, written as a list of coefficients or written as a polynomial in the usual way, is transferred to the values, to the list of values of P at the various places omega to the I. I call this what we get a hat, and then we have a map from A to A hat, which is called the discrete Fourier transform. And in applications, A is often called the signal vector, and A hat is the spectral vector. Sometimes the writing of a polynomial A as a list of coefficients and transferring it to the usual form of polynomials is called a set transform. That's a big thing in engineering, but it's useless because it's strange. Polynomials are just lists of coefficients. And what is the reason to do this transformation from A to A bar? We can make this discrete Fourier transform easier by constructing a matrix D and omega. The first one is just rho. The second one, rho, is just the powers of omega. The third one, the even powers of omega. And I'm sorry about this misprint. The last element in the third row should be 2 times n minus 1. And so on until we reach omega to the n minus 1 and the powers of it. Because what one can do is that the theorem 2 says the transformed, the vector A hat is just easy to get. It's just A times this matrix, this DFT matrix, which means that simultaneous polynomial evaluations become just vector matrix multiplications. Another nice feature is that the inverse of the DFT matrix is basically also of the same type. One has to replace omega by omega minus 1 and divide everything by 1 divided by n. So D is basically self-inverse, and D minus 1 replaces interpolation. It's much faster than interpolation. And it's also very good to work with, because if you have to multiply 2 polynomials, you can use the transformed polynomials dp and dq, and then apply d to the minus 1 to it. So what you can say this, that the discrete Fourier transform translate convolutions into component-wise products similar to what we have seen before. This makes a huge speed up in computing. Adding and multiplying polynomials is of order n squared. After applying d, it gets down to O to the order of n log n. And this is this algorithm of Cooley and Tucker, and some famous algebraists in this area, Gilbert Strang, said already before the turn of the century, this fast Cooley-Tucker algorithm is the most important numerical algorithm in our lifetime. And it's also an important algebraic algorithm, of course. Also, it's very important for applications in engineering because the largest component of the transformed vector A, namely of A hat, gives the most important information on the vector A. And this is often used for data compression. For instance, if you transform big pictures or music, it's very good if you can compress the data before. So we have a diagram of, we go from f of x to f of x factored by f, then to some f to the n, and the return map is, yeah, you can use either the Chinese remainder theorem or interpolation or d to the minus 1. It comes up to the same fact. Observe that the return map, the red one, does not go back to f of x, which would be the wrong address. It goes back to f of x factored by f. So you might get many polynomials at the far end at f of x, which have the same equivalence class as p, but they differ from a polynomial which is higher than the degree of f, and we had excluded that. And this can be also generalized in the following way. One of the most powerful decomposition results is, of course, the Artin-Wedderburn theorem, where you have the possibility to decompose semi-simple rings into full matrix rings if you have the proper finiteness conditions. Now, you can use this also in another way because you can transform other algebraic structures into group rings. For instance, f of x factored by x to the n minus 1 is just a group ring over the cyclic group of order n. And the f of z is isomorphic to the ring of Laurent polynomials in X. And so it's a good idea to shift the interest to group rings. Now, with Maschke's theorem, you get a direct decomposition into simple ideals, and then you can switch on the machinery of representation theory to make everything constructive, to get the orthogonal idempotence and all these things, you know, which I attended this time. For instance, the group ring over the cyclic group of order 3 over the rational field is isomorphic to the rationals direct sum with the polynomials over the rationals factored by x squared plus x plus 1. Or the group ring over S3 over the complex field is isomorphic to two copies of the complex field plus or times the 2 by 2 matrices over the complex fields. And this was done by Thomas Bate, who wrote a book about this Verfahren der schnellen Fourier-Transformation, but unfortunately he has written this in German, and so it's not so popular as it should be, because it also contains a lot of things about general discrete Fourier transforms, because in this matrix rings or direct sums of matrix rings, or in this group rings, you can also develop a similar mechanism as the discrete Fourier transform using the same, or at least similar methods like matrices, block diagonal matrices, which do the transform for you. Now, the next thing is maybe a little bit of daydreaming, which I had some time ago. Can we use parallel computations to get around the Haber-Galois barrier 5, that there cannot be any formulas for solving equations of degree greater or equal to 5? The idea is to do the same, to take polynomials and to decompose the polynomial ring, and to do it in small components, and to glue together these results. So what we are looking for is to find the zero of a polynomial, a solution of the old polynomial equation. This is an element Z, such that the d bar of Z, the corresponding value of the polynomial function, is 0. We can express it in another way. We can say that P composed with Z is equal to 0, where the composition is the composition of polynomials. This is a way to get the concept of solutions of polynomial equations into play, but we see we need a third composition, namely we need the addition, multiplication, and the composition. So what we get is a extension of a ring to a composition ring with 3 operations. Sometimes it's called a 3-operational algebra. And what we are looking for is again to find an ideal. Now these ideals are called full ideals. These are just the kernels of composition ring homomorphisms, and in such a way that the corresponding factor of this composition ring, factored by f, can be decomposed, and so that we can work in factors, and then the factors will have a low degree, and then we'll find zeros there and glue them together again by the Chinese remainder theorem. And now there comes a result which stops this considerations, an old theorem of Neubauer from the 1960s. If F is an infinite field, if and only if the composition ring of polynomials over F is simple. Now that means game over, because in this case we can say we cannot find such a full ideal F as we were looking for here. There doesn't exist one. These composition rings are simple, in the interesting cases. In the finite case, we can always try all candidates because they're finite. But in the infinite case, it would have been so nice if we could have used this decomposition to get around this theorem of Abel and Galois. So what about other decompositions? Let's look at two of them. For instance, the group R factored by the integers with respect to addition is the direct sum of copies of the rationals and of copies of the Prüfer groups of the type CP infinity. Or the decomposition result, every lattice is a subdirect product of subdirectly irreducible lattices. Now, it's much harder to make this more explicit. It would be so nice to have a way to do parallel computations in these cases, but one sees the disadvantage here is that one has sometimes not enough knowledge about the components and usually the way back from the decomposition to the original structure might be very, very hard. And so it's not so constructive as in the examples we have seen before with polynomials, polynomial rings with group rings and so on. Here we cannot lean back and let some, excuse me, some discrete Fourier transforms do the work for us. So as a summary, we can say if you have a decomposition of an algebra A into algebras A sub I, this is, if this should be useful, for instance, for parallel computing, then there are three things you should have. A good map from A to the decomposition, the blue one, and secondly, a sufficiently good knowledge of the components and constructive knowledge of the components so that you can really do computations there. And thirdly, a convenient map back from the decomposition to the original algebraic structure. And so this is, I think, the key of success for some decompositions, that they have all these three ingredients. And if you have a decomposition, then it would be good that you don't simply be happy about this decomposition, but maybe to find a way back from the decomposition to make it into a really useful thing in algebra. So that's about it, and it was it was much easier. This talk was much easier than the previous talks, I think, but I found it very interesting to have different ways to look at decompositions, and so I thank you very much for your attention.
Okay.
Thank you, Guenter.
Yeah.